Okay, well, before we get down to business, I feel like I should say hello. So hi, I'm Amy, and I'm really pleased to meet you all. It's kind of weird meeting an entire room of people like this all at once, but if you want, come up and say hello later. I'd love to have a chat. I am a programmer on the desktop team at GitHub, and we work on GitHub for Mac and GitHub for Windows, and I'm a .NET developer, so I'm working on GitHub for Windows specifically. And today I'm really excited to share with you some things that I've been learning over the past 18 months or so, and it all relates to space, time, and of course, state. When we're writing UI apps, whether it's in WPF, WinForms, actually, is anyone writing apps in WinForms anymore? Yeah, okay, there's a few hands up. So if we're writing apps in WinForms or JavaScript, we're always dealing with the complexities of state. And almost every modern software pattern that we're using today is allowing us to attempting to allow us to separate our concerns, encapsulate, and represent the current state of our application in the least confusing way possible. And over the last few years, I've found myself building a bunch of different GUI apps and a bunch of different technologies. And each time, I feel like I'm asking myself the same question over and over again. Who made this mess? And, and then I get really sad because it was me. So actually, the question that I'm really finding myself asking over and over again is this how I best express what I want my UI to do? And what about this framework? Is it helping me write code that's easier to understand? Are these patterns helping me write less brittle code? Some of the frameworks and patterns that I've used over the years have answered those questions a little bit better than others, but I was always left feeling a little bit dissatisfied with the approaches. All of the techniques had tried to make my code easier to understand and predict, but looking back on it now, they were all just working around the same problem. I'm here to tell you today that you can build UIs that are easy to understand and reason about. You just have to get rid of the very thing that makes your code difficult to predict in the first place, and that thing is state. So you might be wondering, what is state? So I thought maybe we'll take a look. So here we have a class that represents the Starship Enterprise. And for those of you who are not Star Trek fans, sorry, not sorry, try and look past the ship. So this is a class that has some variables describing the current state of the ship. Our shields are down, our weapon systems aren't ready, and we're currently at high warp. We're waiting for a Borg ship to appear. And, you know, if you ask me, I wouldn't be sticking around for one of these things to turn up, but here we are. And once again, once it does appear, we need to update our current state. We need to arm our shields, ready our firepower, and drop out of warp. So any time that we have values like this, variables which we can change through time, be mutated through time, we have state. And that was a really trivial example of state. There was 4 mutable variables, 4 individual states, and each of those permutations, they make up a new state of the starship. But each of those 4 variables, they were mutable, so they could be changed through the course of time. So say, for example, there was a method that allowed the Enterprise to fire its phases, but we could only fire when the phases were actually ready. But the problem is that we're currently awaiting the Borg ship to appear, and our phases aren't ready. So this mutable state has left us in a state that we didn't quite expect to be in. So we've got many possible states, and a lack of predictability, and this is giving rise to complexity in our software. And as software engineers, one of the things that I'm hoping that we're trying to do is build the least complicated systems we possibly can, because in the long run, right, it hurts us. So it follows that if the presence of state and its mutation is giving rise to a certain amount of complexity, then maybe we could try and get rid of it, or at least try and minimize it. So to do that, we're going to try and spot where state typically lives in our traditional imperative user interface design patterns. And specifically, we're going to take a look at the way that we might manage and respond to changes in state when we're building an interface to control a starship's warp engine. So we're going to begin by modeling our warp drive. And because this is only a 30-minute talk, I'm going to gloss over the implementation details of how a warp drive actually works and just define an interface. So suffice to say that a warp drive is a complicated piece of engineering. We need to be constantly monitoring sensor information so that we can use the warp drive efficiently. We need to know what the antimatter containment level is. We want to know how much reactive dilithium crystal we have, and we need to know whether our plasma regulators are active, right? I mean, this is important stuff. So now we're going to create a warp drive view model, which we're going to use to bind to a view of some kind. And this view model is going to need to know about our warp drive model. So we're going to take that in as a dependency. And then in the constructor, we're going to take the current state of the warp drive and assign that to our own internal fields so that we can show and bind those on the UI. So now we have two sets of state. We've got the state of the warp drive and we've got the state of our view model. So how do we make sure that we keep all of those in sync? Well, we use events, right? So let's subscribe to some warp drive events. And when those events are fired, we can use this as an opportunity to update the current state of the warp drive view model. But our warp drive view model also needs to control user interaction. So for example, we need to know whether a button has been pressed or not, or whether it's enabled. And then when it is pressed, we need to know what logic we're going to execute when it is. So we might expose a public property, which is going to allow us to control the enabled or disabled state of a warp drive button in the UI. But we want to make sure that we only are enabled when our warp drive is in a state where it's safe to actually enable that to engage warp. So to determine this, we're going to need to query the current state of the warp drive sensors. Is the antimatter containment level sensor reporting a status above a particular threshold? Are our regulator sensors currently active? How much dilithium crystal do we actually have? So when we're checking values of mutable state like this, generally we're doing it synchronously. We're querying, we're asking, we're pulling the current value out of a property getter. And so you can see that the direction that the data is flowing is pull. So let's keep this in mind, in the back of our mind, when we see what happens when we implement the engage warp drive button. So if all of those conditions are satisfied and the button's enabled, when it's clicked, we want to do some work to engage the warp drive. So we're going to define a method. The first thing we better do is recheck those sensor readings because it might have changed. And if that's okay, then we're going to prepare the warp drive. And if that's successful, then we can finally engage. And hopefully at this point we're at warp and we can update our current speed. But because writing software isn't hard enough, right, we have to deal with asynchrony. Servers take time to respond, file systems take time to write to, and warp drives take a very long time to prepare. I have it on good authority. So we're going to have to await this call. Okay, so let's take a bit of a pause and just check out what we've covered. We've introduced a lot of state in a lot of different places. We've got our model, it's the stateful warp engine. It defined the state of a few different sensor readings, and it had a couple of methods where we could first prepare the warp drive and then engage it into warp. And we also find that other bits of state is mutated as we call those methods, like, for example, the speed that we're currently traveling at. And then we build a stateful view model to mediate the interaction between what's happening in our model and what's expressed on our view. And it held the state of the text to display on the UI readouts and some logic to execute when the button was pressed. And one thing that I haven't mentioned yet is that our views that we're bound to are also stateful, right? Every control that we render on the screen holds some state. Is a button being hovered over? Does it need to render a new style? Is it enabled or disabled? What text is being input into this control right at this minute? And unfortunately for us, especially if we're working with frameworks like WPF, for example, this is not really state that we're going to be able to get rid of, right? This is state that we have to work around. So all of that state is being mutated through time, and because it's mutable, it makes it very difficult for us to predict the course that things might take through our application's life. We can predict some of the paths, but we can't predict them all. It's just too much to hold in our head. When reading a simple property at 2 different times in our application's life can result in 2 different values, like as a consumer, in order to be able to predict that behavior and reason about and react to those possible state changes, we need to know a lot more about the implementation than we really should. And as our state changes, we need to remain informed about those new values so that we can react to them appropriately by raising and subscribing to events. So events, they're a fantastic way of changing that paradigm a little, allowing us to be push notifications of state changes as they occur through time. So events are kind of like a postcard, right? They're snapshots in time. They tell you something interesting has happened and that we have a new state after that thing has happened. So they represent a state at a particular point in time. So if we think about it, what events are really giving us is a way to work with values as they change through time. We're using events to help us mentally model how we process asynchronous data streams. So imagine we're working with those sensor events. What they really are is just streams of values that are arriving at unpredictable times. We're using events to help us mentally model this problem and then integrate those changes back into the stateful object model that we have. So while events have been enormously helpful to us, they've also come with their own set of limitations. And those limitations are important to acknowledge. First, like for me, this is the biggest one, right? Like if we have a large, complicated user interface, the mental model that you have to form to keep track of all of those events, all of those streams of values, is big, complicated, enormous, and frankly, it hurts my brain thinking about them. And to bring it back to the real world for a moment, in an app like GitHub for Windows or Visual Studio or any GUI application, the number of events that we're keeping track of is enormous. You've got events being raised from your UI layer, and you've got events being raised to and from your I/O layer. And in the middle, what we've done is essentially built a Rube Goldberg machine of state and time. The mental model that we have is bound to what states you expect to change and when you expect them to change. And the second problem with events is that they have a pretty serious limitation in that you can't assign an event to a variable, which might sound a little bit weird, but the fact that you can't do this means that you can't easily combine two events together to form a higher order event. So imagine you want to know when both event A and B happens so that you can raise a new composite event, event C. Like, for example, is the warp drive engaged? And have we got new sensor readings from the tactical station to say that a ship's approaching? If that's true, then we want to raise a new event, event C. But we can't do this easily without storing more state. More state, more opportunity for mutation, more opportunity for complexity, and errors. So if we want our code to be more predictable, then perhaps we can solve this problem in a different way. If we can't avoid the state that our UI layer has, and we can't avoid the state that our I/O layer has, then perhaps we can attempt to minimize the state that we carry around in the middle. And we can do this using an idea called stateless core and stateful shell. And it's an idea that I first heard about in this fantastic talk by Gary Bernhardt called Boundaries. And I highly recommend that everyone goes home and watches this talk. It's really good. So the idea is that we keep our core domain logic, all of that stuff that's in the middle, as completely immutable value types. And then we add stateful shell adapter objects around the outside that have mutable references to all of that immutable data. So they're kind of like bridging the gap. So what would an immutable core look like? Well, we saw at the beginning of the talk, we've got this class, the enterprise, and it's modeled a lot like an object-oriented class would be, right? It has some state, it has some behavior, and it mutates that state through time. And as part of making our enterprise work with this idea of immutable objects, one of the things that we're going to have to do is shift the way that we think about this problem. So typically when we're modeling objects, we're trying to get them as close to the real world as we possibly can. We're going to make a shift away from that, and rather than modeling the object, we're going to start to model states that the objects can be in. So we'll take all of that state that our Starship Enterprise has, and we're going to move this into a new class, a class that's first immutable, and second represents a particular state that the Starship can be in. We're going to make all of our fields private read-only fields, which means that they can only be modified at construction time, and it's about as close as we're going to get to immutability in C#. And after that, if we want to transition into a new state, rather than modifying those fields, we're going to expose a way to create a new state, or a way to transition into a new state. So when we want to prepare for battle, we're going to return a new battle-ready enterprise that has its shields up, its phasers armed, and it's not currently travelling at high warp. And what this means is when we're interacting with these states, we're working with immutable objects that are in states that we entirely expect them to be in. At state 1, we're at warp, the Borg ship approaches, we prepare ourselves for battle, and then suddenly we can fire. So it's a lot like the way strings work in .NET. When you concatenate or modify strings, you never get the original one back, you always get a brand new one. So this dramatically simplifies programming because it's simplifying our mental model, because all of the allowable states in a system become values in the system. So in addition to pure, immutable value types, another thing we can do is introduce this idea of pure algorithms or pure functions. And this is another great way to help us eliminate state and introduce predictability into our software. So here's two simple examples of what a pure function might look like. Both of those functions are always going to return the exact same output for the same set of inputs. These functions are predictable and contain within them zero state mutation. Contrasting that to an impure function, where the output is entirely dependent on this mutable field warp count. It makes it very difficult for us to predict and reason about the possible outputs for a given set of inputs. We can chain these pure functions together using link to create higher order pipelines that have no side effects. So here's a class, the damage sweeper. And if you've ever watched an episode of Star Trek, the captain asks for a damage report at least once per episode, hopefully twice, because that's an awesome episode. And I have it on pretty good authority that this is the exact code that they use when they sweep the ship for damage. So it's a pure function that uses link to operate on an enumerable of decks. It flattens those decks out to get each of the sections of the ship, then calls a pure function to determine the damage, and then transforms that into another immutable type that it describes the damaged sections of the ship. So now the question is how do we bridge the gap? How do we bridge the gap between our stateless core and our stateful shell using pure functions and immutable objects? Both the UI layer and the IO layer are raising events in different orders to our stateless core. So we really need to know how we're going to be able to respond to those events in a stateless fashion. So the essence of this question is, how can we statelessly react to events in real time? The wonderful thing is with reactive extensions, we can combine our knowledge of link and our knowledge of pure stateless functions and apply those to asynchronous event streams. So reactive extensions can be loosely described as link to asynchronous data streams or link to events that haven't happened yet. I literally feel like a time traveler when I'm working with reactive extensions. This is my face at my computer every single day. So for example, if we were to take this damage sweeper and we were to make it work with deck reports as they arrive. And if we think about it, it's a little closer to the way that a starship would actually work, right? If we were to ask all of the decks for their damage reports, they would respond independently and they would respond asynchronously. And we want to be able to determine the damage as the reports come in. So we can make this pure function work with observable streams of events. So now what we have is a function that transforms events as they arrive. We don't have to wait for the deck reports to come in. We can sweep the ship for damage completely asynchronously. So how would we take this idea and apply it to transforming events being raised from our stateful shell? How do we interact with an I/O layer that's often very stateful? So for example, perhaps we're interacting with a file system. In GitHub for Windows, our I/O layer is primarily the Git object database. And in a warp drive of a starship, some of the I/O comes from low-level sensor drivers. So here we can see a sensor driver that is able to raise an event each time it detects a new sensor reading. And there's a couple of ways that we could integrate this into our stateless core, and I thought I'd show you just one of them. So if our low-level object is raising events like this, the sensor, we can convert these into observable streams of values by wrapping this in an adapter object of some kind. So we'll create that adapter object, an RX sensor adapter, if you will, and it's going to take that sensor driver, that low-level sensor driver, in as a dependency. From there, we can expose an observable stream of sensor outputs. And we do this by using a helper, a reactive extensions helper called from_event_pattern. And this allows us to teach reactive extensions to convert this events being raised on sensor reading into a stream of values that we can then work with reactively. So once we've done this, we're able to transform that stream of values as they arrive into a new object, sensor output, and this is an immutable object. Then these selects are executed as the sensor readings, as the events are being raised. To interact with that event stream, it's as simple as creating an adapter object, wrapping that grabs that sensor driver, and then subscribing to the notifications of the sensor outputs. So each time we receive a new notification, we're able to print to the console in real time what that value is. So here's a close-up of that happening, because you can't read it on the console on the screen. That's happening in real time. Those are real sensor readings, by the way. That's how a warp drive works, just incrementing values. Yep. We can then use link to filter out and select only the values, the events that we're interested in. So for example, perhaps we want to know if the value is even, and then if it is, we want to transform that into a new value, times it by 100. So if we reach back into our minds, and remember when we built that warp drive model and its view model, it had a ton of state and a ton of mutation. Could we express the same problem using reactive extensions? So let's make this warp drive an observable one. We'll take all of those properties and make each of them return an observable integer of an observable stream of integers. But I think we can actually go one further and make it return a sensor output. Let's be explicit about what that integer actually means. And remember our warp drive view model? Let's pass in our newly reactive warp drive as a dependency. And then using reactive extensions, we can automatically update our UI based on the sensor reading events as they arrive by subscribing to those signals. Our view model contained a property which controlled the enabled or disabled state of a button. Using reactive extensions, we can combine the sensor outputs from different event streams to produce an entirely new event stream, allowing us to react to the sensor readings in real time. So we can combine the event stream of antimatter sensors events arriving with the event stream of dilithium crystal levels, and in real time produce a new set of events that allows us to describe whether or not we're at the threshold for warp. So we can create a new immutable value type that takes two sensor readings and exposes one public method that allows us to determine whether we're running within normal parameters for those particular sensor outputs. So this is an immutable object with one pure function. And using some of the inbuilt RX operators, we can combine the last seen values from the antimatter sensor with the last known value of the dilithium crystal sensor, and we can transform that into a new composite stream of warp drive threshold events. So what this is doing is when either one of those sensor outputs produces an event, it's going to take the last known value from the other to produce a new event stream. So from there, enabling the warp drive button is really simple. We're able to subscribe to that new composite event stream in our view model. If we're able to take that and then select out whether or not we're running within normal parameters, we can then use the result of that to describe whether or not our button is enabled or not. And last but not least, let's express engaging warp as a pipeline of immutable and pure functions. So we're going to scroll down till we find the placeholder method. Engage warp. So the first thing we need to do is prepare the warp drive. Now this prepare method is going to return an immutable prepared warp drive. So we're not mutating the state of a warp drive, we're just transitioning into a new state. From there we can engage the warp drive and then update our current speed on the UI. Now another way that we could do this is this current speed object could be pumping out events as well. So we could wire up in our constructor another subscription to update that speed independently of this function. So there you have it. That was Reactive Warp. We've taken our Rube Goldberg machine of state and time and we've converted it into stateless, immutable reactive pipelines reacting to and transforming events in real time. Our code has become the stateless world inside a stateful shell. And immutability and pure functions have helped us minimize the amount of state that we lug around with us. We've reduced the complexity and the unpredictability of our UI. And using reactive extensions, we can apply these ideas to events as they occur in real time. If you're interested in diving deeper into this idea of statelessness, I'd recommend that you watch this talk that I mentioned earlier. You can find it on Destroy All Software. And if you're interested in diving deeper into reactive extensions, I'm currently doing a screencast on reactive extensions. There's one episode up, and there'll be another episode up later in the week. So thank you very much for coming to listen to this talk. I'm Amy, and you're awesome.
So we have 3 minutes for questions. If anyone has any question.
Hi. It should be on. All right. So the immutable object pattern. One of the things that we struggle with is, kind of creating the number of classes, because when you have state, it kind of starts to combine, and the number of states explode very quickly. So it becomes easy. There's a pressure there to put the mutable state in something and just kind of pass that around. And the alternatives are like code gen or just writing a bunch of code yourself. So I'm wondering if you have any insight into how to manage that explosion.
I mean, other than creating a lot of classes and dealing with the thing that you talked about of that explosion of state, I mean, I'm not really sure of what the best ways are to manage that. I mean, I guess one way you could manage it is create containers of state, right? So like subsystems within systems, if that makes sense. So you're only exposing the states that you really need to interact with, but you still have the state, right? So I guess the answer to that would be stateless, which is not very helpful to you if you have state. Sorry.
There we go. Okay. Any more questions? We've got time for maybe one more. Yeah. Also, if there was anything you missed, the talks are recorded, and we'll be releasing that shortly after the conference. All right. Well, thanks so much, Amy. Yeah, we're going to break for another 10 minutes or so, and then we'll be back with a couple more talks. So stretch your legs.